At the end of this video, you should be able to define valence electrons and state how many are present in atoms of each main group element, and compare the atomic radii, ionization energies, and electronegativities of the d block elements with those of the main group elements. Chapter 5, Section 3, Valence electrons. Chemical compounds form because electrons are lost, gained, or shared between the atoms. The electrons that interact in this matter are those in the highest energy levels. These are the electrons most subject to the influence of nearby atoms or ions. The electrons available to be lost, gained, or shared in the formation of chemical compounds are referred to as valence electrons. Valence electrons are often located in incompletely filled main energy levels. For example, the electron lost from the 3s sublevel of sodium to form an Na+1 ion is a valence electron. For main group elements, the valence electrons are the electrons in the outermost s and p sublevels. The inner electrons are in filled energy levels and are held too tightly by the nucleus to be involved in compound formation. The group 1 and group 2 elements have 1 and 2 valence electrons respectively, as is shown in table 5-4 on page 150 of your text or on the screen now. The elements of group 13 through 18 have a number of valence electrons equal to the group number -10. In some cases, both the s and p sublevel valence electrons of the p block elements are involved in compound formation. In other cases, only the electrons from the p sublevel are involved.
Valence electrons are the electrons outside the outermost complete energy level. In oxygen, the first energy level, which can hold 2 electrons, is complete. The second energy level can hold 8 electrons, but oxygen only has 6. All of these are valence electrons. In this sodium atom, the first and second energy levels are full. The third energy level is not full. Sodium has only a single valence electron. Noble gases such as neon rarely react because all of their energy levels are complete. They don't have any valence electrons to participate in a reaction. The number of valence electrons for s and p block elements can be determined from the periodic table. For example, all members of the alkaline earth metals have 2 valence electrons, and all members of the nitrogen group have 5 valence electrons.
Electronegativity. Valence electrons hold atoms together in chemical compounds. In many compounds, the negative charge of the valence electrons is concentrated closer to one atom than to another. This uneven concentration of charge has a significant effect on the chemical properties of a compound. It is therefore useful to have a measure of how strongly one atom attracts the electrons of another atom within a compound. Linus Pauling, one of America's most famous chemists, devised a scale of numerical values reflecting the tendency of an atom to attract electrons. Electronegativity is the measure of an ability of an atom in a chemical compound to attract electrons. The most electronegative element, fluorine, is arbitrarily assigned an electronegativity value of 4. Values for the other elements are then calculated in relation to this value. Period trends. As shown in figure 5-20 on page 151 of your text or on the screen now, electronegativities tend to increase across each period, although there are some exceptions. The alkali and alkaline earth metals are the least electronegative elements. In compounds, their atoms have low attraction for electrons. Nitrogen, oxygen, and the halogens are the most electronegative elements. Their atoms attract electrons strongly in compounds. Electronegativities tend to either decrease down a group or remain about the same. The noble gases are unusual in that some of them do not form compounds and therefore cannot be assigned electronegativities. When a noble gas does form a compound, its electronegativity is rather high, similar to the values for the halogens. The combination of the period and group trends in electronegativity results in the highest values belonging to the elements in the upper right of the periodic table. The lowest values belong to the elements in the lower left of the table.
Electronegativity is a measure of the ability of an atom in a chemical compound to attract electrons. It is measured on an arbitrary scale of 0 to 4, developed by Linus Pauling. Fluorine has the strongest ability of any element to attract electrons from other atoms. For elements in the same period, the ability to attract electrons decreases as the number of filled orbitals decreases. The hydrogen atom has only one electron. It is almost equally likely to attract from or give up electrons to other atoms. As atoms get larger, the distance from the outer electrons to the atomic nucleus increases. The ability of these atoms to attract electrons to their outer orbitals decreases.
Periodic properties of the D and F block elements. The properties of the D block elements, which are all metals, vary less and with less regularity than those of the main group elements. This trend is indicated by the curves in figures 5-14 and 5-16, which flatten where the D block elements fall in the middle of periods 4 through 6. Recall that the atoms of the D block elements contain from 0 to 2 electrons in the s orbital of their highest occupied energy level, and 1 to 10 electrons in the d sublevel of the next lower energy level. Therefore, electrons in both the ns sublevel and the n-1d sublevel are available to interact with their surroundings. As a result, electrons in the incompletely filled d sublevels are responsible for many characteristics of the D block elements. Atomic radii. The atomic radii of the D block elements generally decrease across the periods. However, this decrease is less than that for the main group elements because the electrons are added to the n-1 d sublevel and they shield the outer electrons from the nucleus. Also, note in figure 5-14 that the radii dip to a low and then increase slightly across each of the 4 periods that contain D block elements. As the number of electrons in the D sublevel increases, the radii increase because the repulsion of the electrons. In the 6th period, the F block elements fall between lanthanum, group 3, and hafnium, group 4. Because of the increase in atomic number that occurs from lanthanum to hafnium, the atomic radius of hafnium is actually slightly less than that of zirconium, Zr, which is the element immediately above it. The radii of the elements following hafnium in the 6th period vary with increasing atomic number in the usual manner. Ionization energy. As they do for the main group elements, ionization energies of the D block and F block elements generally increase across the periods. In contrast to the decrease down the main groups, however, the first ionization energies of the D block elements generally increase down each group. This is because the electrons available for ionization in the outer s sublevels are less shielded from the increasing nuclear charge by electrons in the incomplete n-1 d sublevels. Ion formation and ionic radii. The order in which electrons are removed from all atoms of the D block and F block elements is exactly the reverse of the order given by the electron configuration notation. In other words, electrons in the highest occupied sublevel are always removed first. For the D block elements, this means that although newly added electrons occupy the D sublevels, the first electrons to be removed are those in the outermost S sublevels. For example, iron, Fe, has the electron configuration of argon 3d6 4s2. It loses a 4s electron first to form Fe plus 1 with a configuration of argon 3d6 4s1. Iron 1 plus can then lose the second 4s electron to form Fe2 plus, which has a configuration of argon 3d6. Fe2 plus can then lose a third electron, a 3d electron, to form Fe3 plus, which has a configuration of argon 3d5. Most D block elements commonly form 2+ ions in compounds. Some, such as iron and chromium, also commonly form 3+ ions. The group 3 elements form only ions with a 3+ charge. Copper forms 1+ and 2+ ions, and silver usually forms only 1+ ions. As expected, the cations have smaller radii than the atoms do. Comparing 2+ ions across the periods shows a decrease in size that parallels the decrease in atomic radius. Electronegativity. The D block elements all have electronegativities between 1.1 and 2.54. Only the active metals in groups 1 and 2 have lower electronegativities. The D block elements also follow the general trend for electronegativity values to increase as radii decrease, and vice versa. The F block elements all have similar electronegativities, which range from 1.1 to 1.5. At this point, you should be able to define valence electrons and state how many are present in atoms of each main group element, and compare the atomic radii, ionization energies, and electronegativities of the D block elements with those of the main group elements.